Okay. Now I'm recording. Okay.
Because if
Now
you
you
had
need to
all
record.
zeros.
Do what?
Now you need to record this.
Thank you.
Because if you had had all zeros, it would have been all the numbers.
If this had been a 0, is that what you're saying?
Right, yes, ma'am.
If this had been a 0, then it would not have mattered what H was. That's correct. Okay, anything else? Nothing else? Okay, then. Section 1.2. We are going to look more about the row reduction process, which is the way we're going to solve these equations. So I'm going to go between here and working problems. But we're still talking about the system. What are you doing to solve a system of equations? How do you row reduce this matrix, and some more terminology? All right, first of all, a non-zero row or column of a matrix is a row or column that has at least one non-zero entry. Or does everybody know what that means? You have to have a row or a column that's not all zeros. If they're talking about a non-zero row, it can have some zeros, but it's got to have at least one other number in there, okay? A leading entry of a row is the leftmost non-zero entry in a row, in a non-zero row. Maybe. Okay. Now, we are going to be putting our matrices in something called echelon form. So echelon form has 3 properties. All non-zero rows are above any rows of all zeros. So any row that's got all zeros has got to be at the very bottom of your matrix. Step 1. Step 2. Each leading entry of a row is in a column to the right of the leading entry of the row above it. Which means, all right, if this is, let's say, that's a number, those are zeros. The leading entry of a row is to the right of the one above it. So in this next row, my first non-zero number has got to be over here. It can't be to the left. It's going to be kind of in a stair step. So the leading entries are to the right of the entry above it. To the right of the entry above it. And all entries in a column below a leading entry are all zeros. Leading entry, everything below it's got to be 0. Leading entry, everything below it's got to be a 0. Leading entry, everything's got to be a 0 below it for it to be in echelon form. Staring at me like it's not making sense. So let's see if I can make it make sense. All right, here are some examples in your book. All right, these matrices are in echelon form. These rows of all zeros are at the bottom. The leading entry, that's to the right of the one above it. Okay? And underneath the leading entry is all zeros. All zeros, all zeros. In this one, okay? There's no row of all zeros, but if it were, it would be at the bottom. These are called pivots. The leading entries, that is to the right of the one above it. That's to the right of the one above it. That's to the right of the one above it. That's to the right of the one above it, okay? And underneath all of these are zeros. This is a 0 column. You don't move columns, okay? The 0 column can be there if it has to be. Does that make sense?
There's a square column and then there's a star column.
This stands for your leading entry.
Okay, right, it's your leading
So
entry.
just put the square because it's a leading entry. The star just means there's other numbers out there. Okay?
It can be any number.
Out here, these, yeah, this can even be any number. If it's an echelon form, this can be a 1, it can be a 4, it can be a -7.
Well,
And these can be anything either.
The asterisk can be any number, including 0.
Correct.
The boxes can only be
Numbers.
Numbers.
Non-zero numbers. Non-zero. Okay? So that's called echelon form. Then we have something called reduced echelon form. And that's two more things have to happen for reduced echelon form. If it's reduced echelon form, those little blocks had to be all 1. Reduced echelon form means those pivots, those leading entries are 1. And each leading entry is the only non-zero entry in its column. That means not only do you have zeros below it, but you have zeros above it for it to be reduced echelon form. So if we were looking at some of those, it would be down here. Again, 0 rows at the bottom. The pivots or the leading entries are 1, and under that 1 are zeros, above that and below that 1 are also zeros. This is reduced echelon form.
So it doesn't have, the zeros don't have to be above 1, but it just has to be either above or below?
No, it doesn't. If there's a row above a leading entry, then that's got to be a 0.
Okay.
Has to be a 0 for it to be a reduced echelon form. This is a leading entry, so you have to have zeros above it, you have to have zeros below it. That's a leading entry, you have to have zeros above and below.
Is that 1 on the second column, is that a leading, the second column?
Which is that one. That's a leading coefficient, but there's no row above it, so it's, there's nothing above it to be a 0.
Okay, but we still consider it.
Yeah, that's leading, that's leading. This has got 1, 2, 3, 4, 5 leading coefficients. They're all to the right of the ones above it. Above and below are all zeros. Okay? And this is called echelon form or reduced echelon form. All right, see if, back here on these homework problems, down here at the bottom. In this exercise, can we decide which matrices are in reduced echelon form and which are just echelon form? Well, they may be neither. Are you following me? All right, so look at this one. Number A, you're trying to decide, is it reduced echelon form, is it just echelon form, or maybe it's none of the above. What do you think?
Reduced.
It's reduced. Reduced echelon form. Your pivots are all 1s. Below and above are all zeros, and they're all to the right. It's reduced echelon form. What about this one? Why is this just echelon?
Because it has a 1 above the third column, leading. Like there's a 1 on the third, like there's not a 0 above.
Okay. There's not a 0, but is that a leading coefficient? All right, so that's leading, got zeros. That's leading, zeros. That's leading, and it's got zeros. It actually is in reduced echelon form. Yeah. If it's not a leading coefficient, it can have something above it. Is everybody following? All right, what about this one? C. Is it echelon, reduced echelon, nothing? Because? Right, this row of zeros should be at the bottom for it to be an echelon or reduced echelon, so it's not either. And this one, I'm not sure, what's that one? Okay, what about that one? It is what? You're right. It is echelon, but it's not reduced. Does everybody know why? It's not reduced because you don't have 1s, but it is an echelon form because, remember, there were 3 things. The non-zero have to be to the right of the ones above it. These can be any number, and they have to have zeros below them. So it's echelon, but just not reduced. Okay?
What was A and B? I'm sorry, I didn't.
What was A?
What were A and B? Reduced echelon.
I think both of these were reduced.
Both of them reduced.
Mhm. Okay. The echelon is one is, an echelon matrix is one that's echelon in form. Well, sure you figured that out. Okay. Any non-zero matrix can be row reduced into more than one matrix that's in echelon form using different sequences of row operations. But reduced echelon is unique. All right, think about it. We could all take a matrix in here and get a valid echelon form and that all look different. But if we finish the problem and put it all the way to reduced echelon form, there is one of those. We'll all get the same thing. Reduced is unique, but echelon form is not unique. And that's all this theorem says. Each matrix is row equivalent to one and only one reduced echelon matrix. Now this is something you could see in a true-false question. They could take out this word right here, and then it would be false. Right?
What did you say was unique and which one wasn't?
Reduced echelon is unique. Echelon is not unique. Okay. All right, now let's go through some of this. If a matrix is row equivalent to an echelon matrix U, then U is an echelon form of A. And if U is reduced echelon, we say it's a reduced echelon form of A. A pivot position, I was using the word pivot position, okay, is the location that corresponds to the leading one in the reduced echelon form. And a pivot column is one that contains a pivot position. I'll explain a little bit better in a second. All right, they're going to take this one, then I'm going to take one and do the same thing. So just don't stress too much. I'm just showing you what they do. Row reduce the matrix to echelon form. Locate the pivot columns. Okay. So if we're going to simplify this to echelon form, you've got to try to get a leading coefficient up here. Okay, so they need to swap one of these rows and get something beside a zero up here because your first pivot needs to be up there. So you could actually interchange any of these rows. I think they interchange 1 and 4 to get the 1 up there. Okay, so they interchange 1 and 4. All right, you're trying to get it to echelon form, so what do you think the next, okay, don't look at that. All right, trying to get it to echelon form, what do you think the next step would be for you? Once you've got that pivot right there, what are you going to try to do?
Zeros below it.
You're going to get zeros below it, exactly. So you would multiply 1 times this, well, you just multiply 1, add those two together, right? And then for this one, you'd multiply 2 times this one and add it together. And you get all zeros under there. That would be your first pivot and a leading coefficient, right? Then what you're going to do, this is your next pivot. It's got to be to the right. You try to get zeros under there. They didn't say reduced echelon, they just said echelon form, so this does not have to be a 1. They're going to try to get zeros under here. Okay, so they did that. And this is what happened. That whole row zeroed out.
It goes to the bottom.
So it's got to move to the bottom. You've got to interchange these two to move to the bottom. So this next pivot is going to move up and be right here. So here's the pivot, here's the pivot, here's the pivot. You following me? All right, now it is in echelon form. You've got your pivots. You've got zeros under your pivots. So the pivots are called pivot columns. That's what they asked us to find. Are 1, 2, and 4. Okay, 1, 2, and 4 are your pivot columns. And then they went back to the original matrix and circle 1, 2, and the 4th place right there. And these are the pivot numbers. Okay? Now we'll work one for you. Would that help if I work one? Okay. And look at me, I wrote down a problem. So I wouldn't even have to write it. All right, here's a matrix. I don't like the numbers at all. But this is out of your book, number 3 out of your book. Oops, wrong one. All right, here's a matrix. They want us to circle the pivot position in the final matrix and in the original matrix. List the pivot columns. So we're looking for pivots. I have to pull out a calculator here, but we're looking for pivots. All right, so you guys help me out. I don't have to interchange any rows because I've already got something right there. So what am I going to do? Zeros underneath here. So I'm going to multiply, what I would multiply -4 times row 1 and add it to row 2. 1, 2, 3, 4 does not change. -4 and 4 is 0. -8 and 5 is -3. -12 and 6. -16 and 7, I believe, is -9. Now please check my arithmetic, okay? All right, then I would go ahead and get rid of this 6, so I would multiply -6 times row 1 and add it to row 3. So that's a 0. -12 and 7 is -5, I believe. -18 and 8 looks like -10. -24 and 9, is that -15? Okay. Yes? Okay. All right, we're not going, they didn't tell us to get reduced echelon form, they just said echelon form. And it's not unique. So you've got a lot of choices on what you want to do. What do you want to do to try to get this in echelon form? You're going to have to get a 0 right here. I'm not liking that 3 and that 5, but you can do it. Would y'all want to divide all that by -3? Or y'all good with whatever it is? It doesn't matter. Let's get rid of that, since y'all are leaving it up to me. I would multiply -1/3 times row 2. So that's going to be 0, 1, 2, 3. And you could just leave this here. And then what I have to do is try to get a 0 right here. So I would multiply 5 times row 2 and add it to row 3. You ignore row 1, remember? You ignore that one. 1.
Does that get rid of your entire bottom line?
Probably so, because that's going to be 0, 0, 0, 0. Okey-doke. It did. It got rid of the whole thing. In echelon form, if I've got a row of all zeros, it has to be at the bottom. It's at the bottom. Is there anything else I need to do then for echelon form? No. I needed to find my pivots. Here is the pivot in this row. Here's the pivot in this one. So my pivot,
Is 1 and 5?
pardon?
1 and 5. Does that do that?
Oh, yeah, you were going back to the original. Yeah, because they want me to circle in the original matrix. I have to circle the pivot position in my final matrix. There's my pivot positions here. Circle the pivots in the pivot positions in the original matrix. And list my pivot columns. My pivot columns are column 1 and column 2. Those are my pivot positions and my pivot columns. This matrix right here is not unique. We could have all reduced it and gotten it in a different form, but we would still have gotten the same pivot positions. question.
And you leave out the pictures, you can leave them right
Oh,
there,
I
that's
would
fine,
have.
but
My notes are always going to be up here. You can always get them, take pictures after class. That's another idea too. Okay. Now, what do they want us to do here? Apply elementary row operations to transform the following matrix first into echelon form and then into reduced echelon form. All right, we've got a choice here. I'll give you a choice. I can go through their slides and do this, or I can copy this down and do it and explain it as I go. You want me to copy it down and explain it as I go? Okay. Well, let me copy it down. 0, 3, negative 6, 6, 4, negative 5, 3, negative 7, 8, negative 5, 8, 9, Y'all got it copied down? Okay, then you better check and make sure I copied it right. 'Cause this is the one we're fixing to do. Did I get the same thing, copy it, the same thing y'all did? Okay. And all they want me to do is first put it in echelon, then reduced echelon. So we're going to echelon form because that's the idea, that's what we're going to be doing. You know, basically the rest of the semester is going to reduced echelon form, okay? All right, so you have to get a pivot up here. So we need to interchange one of those rows, and it doesn't matter which one. Y'all have a preference on which one? I think I'll put this one. I'm going to permute rows 1 and 3. Three, negative 9, 12, negative 9, 6, and 15. 2 stays the same. 3, negative 7, 8, negative 5, 8, 9, and then this is 0, 3, negative 6, 6, 4, and negative 5. Okay, I'm headed to reduced echelon form. What I would do, when I was writing this, I noticed that everything up here could be divided by 3. So I probably would go ahead and divide everything by 3 just to make my numbers smaller. Okay, but that's just me. So this would be 1, negative 3, 4, negative 3, 2, and 5. This is 3, negative 7, 8, negative 5, 8, 9, 0, 3, negative 6, 6, 4, and negative 5. All I was supposed to have done is multiply 1/3 times row 2. Nope, times row 1. Right, that's all I did right there. So far I've permuted and I multiplied 1/3 times row 1. Okay, I need to get a 0 in this position right here. All right, multiply negative 3 times row 1 and add it to row 2. Does row 1 change? No. Just rewrite it. All right, negative 3 and 3 is 0. 9 minus 7. Negative 12 and 8. 9 minus 5 is 4. Negative 6 and 8 might be a 2. Negative 15 and 9. Maybe a negative 6. 3, negative 6, 6, 4. All right, did y'all check my arithmetic? Anybody? Okay. Okay, so now I have zeros under this pivot, so there's a pivot. What is my next step?
You need to go 3 on like the 3rd row.
Right, I need to deal with this. I need to get a 0 right here because this is now going to be my next pivot. Here was a pivot. That's my first non-zero entry. That's going to be a pivot. I noticed also that all of that could be divided by 2. So I would probably go ahead and divide that by 2, just because multiply by 1/2. So 1/2 times row 2. So you have 1, -3. This row does not change. 1/2 times row 2 is 0, 1, -2, positive 2, 1, and -3. Okay. So pivot, pivot. I need to get rid of the 3. So you ignore the first row. Ignore it. You're dealing with the second row and that number right there. So I need to multiply -3 times row 2 and add it to row 3. Again, ignoring row 1. 0, 1, -2, 2, 1, -3. 0. -3 and 3 is 0. 6 minus 6 is 0. -6 and 6 is also 0. -3 and 4 is 1. 9 minus 5, I believe, is 4. This is now echelon form. Okay, I'm just going to write that. And why is it echelon form? Because zeros are under my pivots, and all of them are to the right of the other ones, the ones above them. Okay. So so I've got my pivots. Here's a pivot, here's a pivot, here's a pivot. So those are my pivot columns. Now what I have to do is get zeros above those. This is the forward phase of this. I reduced it to echelon form. This is called the forward phase of the process. Okay, because I got an echelon form. Now, I'm going to now put it in reduced echelon form. I've got my 1s, so I need to get zeros above it, and to work backwards, you start at this last pivot and get zeros above it. So going down here, I need to turn these into zeros. So I'm going to multiply -1 times row 3 and add it to row 2. So now I'm working back up. I worked the forward phase, now I'm working the backward stage. All right, so 0, 0, 0, 0, 1, 4. 0, 1, -2, 2. Nothing changes until I get down here. -1 and 1 is 0. -4 and -3 looks like -7. Okay. Now, before I write down this next one, I'm going to go ahead and get rid of the number in front of it, above it rather. This is going to needs to be a 0. So now I need to multiply -2 times row 3 and add it to row 1. So that's a 1, a -3, a 4, a -3. Nothing changes until I get above this one. -2 and 2 is 0. -8 and 5 looks like -3. Are y'all still with me?
Oh, right there where you,
Yes.
mid-step, you done the other multiplication, and how did you notice to do that? Just
How did I know to do this one right here?
correct, yes.
Okay, because everything above this one, those numbers right there have both got to turn into zeros. Okay. When I did this first one right here, it turned that into a 0.
And the
Okay.
2 was still.
And the 2 was still there because I hadn't done anything to that row yet. So that to get rid of that one, you multiply -2 times this one and add it to this one. Okay. All right. Now, moving backwards, here's my next pivot. Above this pivot has got to be a 0. So to make this turn into a 0, you multiply 3 times row 2 and add it to row 1, because you're looking at that second pivot right there. So the bottom row does not change. The second row does not change. The only thing that's going to change is this top row. The 1 doesn't change. 3 times 1 is 3. 3 minus 3 is 0. Negative 6 and 4 is negative 2. 6 minus 3 is 3. That's still a 0. Negative 21 and negative 3 looks like negative 24. Now, you look to make sure you've got 1s as your pivots, and above and below are all 0s. And they are, and I should have gotten the same, whether I did it the same way the book did or not, doesn't matter. I should have gotten to the same answer that the book got. That's the row reduction algorithm that we're doing. Does that make any more sense today than it did the other day?
There was no.
That's what I thought. All right, let me see what else I need to pull out of this before we look at other problems. All right, they went through here, they did this, and let's see if they get the same answer I do.
So what we just did was that was the backward phase.
Yeah, that's the backwards phase. And
Ms. Travis, for
Yes,
once,
yeah.
that the example in your PowerPoint was the same as the example in the book.
I think it was, wasn't it?
Before it hadn't been, but that
yeah,
one was.
sometimes it is and sometimes it's not. I don't know why, it's just the way it is. All right, but they should have gotten the same answer that I did.
Mm.
And it looks like they did, even though I was noticing when I flipped through it, they went through the process a completely different way because they had a 72 or something way up here that I didn't have.
Yeah,
Okay.
they didn't clear out
The 3, divide by 3.
Until the end.
Right. Okay, but see, I like smaller numbers, so I'm dividing it if I can. So you've got the forward phase, it gets it to echelon. You've got the backwards phase, it gets it to reduced echelon form. All right, so what is this? Okay, there's good true-false questions in here. The row reduction algorithm leads to an explicit description of the solution set of a linear system when the algorithm is applied to an augmented matrix. You remember what augmented is, right? Okay. Suppose, for example, that the augmented matrix of a linear system has been changed to this reduced echelon form. See, this is reduced echelon form. This is augmented, so pretend like it's got this. Okay. We can take this and write the explicit solution for this system, and I'll show you what they do. They change it back to the equation. This is your x sub 1 column, this is your x sub 2 column, this is your x sub 3 column. So this says 1 times x1 minus 5 times x3 is equal to 1. And this says x2 plus x3 is equal to 4. So that's what they did. Okay? Now, those pivots were important because they go or correspond to your what's called your basic variables. Go back here. These are your pivots. This x sub 1 is a basic variable. X sub 2 is a basic variable because they have pivots associated with them. X3 does not have a pivot, so it's what we call a free variable. X1 and X2 are basic, X3 is free. Basically, it's free to be anything you choose it to be. There are no restrictions on X sub 3. Okay. I'm going to show you an example in a minute. Don't freak, okay? All right. That was the solution of a consistent system. All right, that's going to have a solution. When a system is consistent, the solution set can be described explicitly by solving the reduced system for the basic variables in terms of the free variable. This operation is possible because the reduced echelon form places each basic variable in only one equation. And what you need to do is solve the first and second equations for x1 and x2 and ignore the third one. So then what they're going to do is they're going to take that first equation that they have, they're going to solve it for your basic variable. x1 is equal to, x2 is equal to, x3 is free. x3 is free to be anything you want it to be. In this case, they chose x3 to be 1. If x3 is 1, then x1 is going to be 6. If you have 1 there, x2 is going to be 3. And x3 is 1. And I'll do an example. If you chose x3 to be 0, if that were 0, then this would be 1, 4, 0, and it would give you another point, 1, 4, 0, that solves that system. Okay, these are called parametric descriptions of your solution set. I'm going to use that word in here and in calculus. Parametric solution, parametric description. Solving a system amounts to finding a parametric description of the solution set or determining that it is empty. Whenever a system is consistent and it has free variables, then the solution set has many parametric descriptions. The parametric descriptions are not unique. So I'm going to get back to this. Do you understand that this system does have an infinite number of solutions? Because x3 could be anything I choose it to be. It has an infinite number of solutions. What would it have looked like if I had gotten only one solution? Do you know? It would be a number. You would get x1 is equal to 4, x2 is equal to 5, x3 is equal to 6. You would have no free variables.
It would be a 1 and 6.
It would be 1 point. Okay.
Which one did you say? Which one did you say was not unique? So one.
That.
Parametric
Excuse me.
variable or parametric
This is not unique.
Okay.
It has a lot of this is the way you're going to write it. You have to write it my way and the book's way. For us, it's going to be unique, but actually, I could solve this for a different variable, and then it would not be it would be the same solution set written in a different way. But we're always going to solve for our basic variables, so ours is always going to be the same. If that makes any sense, I'll show you in a minute. And here they show. Here they do it. All right, look at this one. This is important. Whenever a system is inconsistent, the solution set is empty, even when the system has free variables. It might have free variables, but it also might be inconsistent. In this case, the solution set has no parametric representation. Let me just show you some examples. All right, well, let me go ahead and go through this, and then we'll just get to the book. All right, here's what we've talked about already this semester. If you have a system, and it's augmented, and you get zeros equal to b, that means it is inconsistent, right? All zeros augmented equal to b is inconsistent. If it is consistent, you may have either a unique solution, or when there are no free variables, or you will have infinitely many solutions when there is at least one free variable. I don't know where theorem 2 is, but it's in your book. In bold, probably in. Okay. So you have no solution, which will show up like this. You have one solution, or you have free variables, and you'll have infinite number of solutions. All right, this is the process you go through to solve the system. I'm going to go through the process one more time. Write the augmented matrix of the system. Use row reduction to get an augmented matrix in echelon form. Decide if it's consistent. If it's consistent, then you keep on going. If it's not consistent, you stop. If it's consistent, you continue to get it reduced echelon form. Then you write your equation in parametric vector form. Or, excuse me, I shouldn't use that word, in parametric form.
Throwing in more words.
I threw in a word that we're not ready for yet. Okay, let me look at some problems out of the book. Okay, suppose I look at number 10. Oops. Do you have questions before I look at something? You don't know if you have questions or not, probably. All right, let's look at number 10. Here is a matrix 1, -2, -1, 3, 3, -6, -2, +2. This is augmented. Find the general solution of the system that represents this augmented equation. What size is this matrix? It's a 2x4 matrix. Okay, just checking. All right, so to solve the system, I want to do what? Okay. -3 times row 1 and add it to row 2, which does not change this one. -3 and 3 is 0. 6 minus 6. 3 minus 2 looks like a 1. -9 and 2, is that -7? Okay. Can you tell if we're going to have a solution or not? You should be able to. Yes, you're going to have a solution because you did not get 0 right there, so you have a solution. So what's the next step? I need this to be a 0 right here. So all I have to do is add row 2 to row 1. This is the forward phase. Now go backwards. So 0, 0, 1, -7, 1, -2. If I add that, I get a 0. If I add that, I get a -4. All right, it's now in reduced echelon form. Everybody good with that? So now I have to write the solution. So I'm going to rewrite an equation. This is my x1, x2, x3. So this says x1 minus 2x2 is equal to -4. This says x sub 3 is -7. Are y'all with me? Where were your pivots? There's a pivot right there for x1. There's a pivot right there, which is your x3. Those are the two things you have to solve for. So I need to rewrite this one, x1 equal to. So x1 is equal to 2x sub 2 minus 4. X sub 3 is equal to -7. X sub 2 has got to equal something. What is it? It is not a basic variable because the basic variables are these two. This one is a free variable, so x2 is free. And I usually write these in order. I write something for x1, something for x2, and something for x3. This represents all of the solutions of this thing. Does everybody understand that? If I ask you to list me a couple of solutions, what could you do to list me some actual solutions? No, you don't have to do that. All you have to do is pick values for x2. So choose, if you wanted to list some solution, choose values for x sub 2. So maybe let x2 be 0. If x2 is 0, then x1 is going to be -4, x2 is 0, x3 is always -7. It doesn't change. So that gives you -0, 4, -4, 0, I'm sorry, and -7. There is 1 point. How could I get another? I could choose x sub 2 to be 1. If it's 1, then x1 is going to be 2 minus 4, which looks like -2. x3 is still -7, so it looks like I'd get the point -2, 1, -7. And that would be another solution to that equation. Do you need me to do another one?
Come on, a whole nother problem.
Pardon? Yeah, I meant a whole nother problem, not another point, a whole nother problem.
No, I'm
Please,
sure.
I
I
mean,
was gonna say
I
sure.
want another one, please. I'll see if you want to.
I'm gonna worry about what everybody else thinks.
Okay. Let's, just for fun, and I don't know what's going to happen with it, let's look down here at number 13 because it's a big matrix. It's going to take me a minute to write it down. 1, -3, 0. -1, 0, -2. 0. And then all zeros. It is augmented. They've done a lot of work for me here. In fact, they've done pretty much the forward phase. Because they've got my pivots. There's a pivot, there's a pivot, and there's a pivot.
You do row 3 added to row 1.
Exactly. I need to get a 0 above that. They've done the forward phase. I need to do the backwards. So I just need to add row 3 plus row 1. So the bottom one is all zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 0, 0, 0, 1, 9. I bet you can't see it. All right, so add 3 and 1. So that's a 1, -3, a 0, 1 and 1 is 0. Oops, did I mess up?
You missed it.
I sure did. I'm missing something. That's a big problem. Sorry. I was thinking it didn't look right. Now that's right, right? 0, 1, 0, 0, -4, 1. Still adding 3 and 1 to get a 1, a -3, a 0. That's a 0. That's a 9. 4 minus 2 is a 2.
You do 3 times row 2 to make,
Okay.
add it to row 1.
3 times row 2 added to row 1. All right, let's see. Still zeros. All right. 3 minus 3 is 0. That's a 0. That's a 0. -12 and 9 is -3. Where am I? Oops, did I do the wrong one? Yep. 3, no, row 2. 3 and 9, is that 12? Wait a minute. I got off, sorry.
No, it's 2 above that.
So that's 3 and 2, which would be 5. Sorry, I got off. All right, your pivots. Here's a pivot, here's a pivot, and here's a pivot. So those represent where my basic variables are. And now I hope y'all checked my math. I think y'all were checking on me, weren't you? Okay, thank you. All right, so this one, there are lots of variables. x1, x2, x3, x4, and x5. So this says x1 minus 3x5 is 5. This one says x2 minus 4x5 is 1. And this one, x4 plus 9x5 is 4. Okay, I've got 3 basic variables. So I solve for those 3 things. Everything else will be free. So for x1 is 3 x5 plus 5. X sub 2 is 4 x5 plus 1. I write something for everything. I don't have, x3 is not a basic variable, so it is free. x4 is a basic variable. x4 is negative 9x5 plus 4. And I have to have something for x5. I've got 5 columns. x5 is also free. This is the parametric representation for the solution. It has an infinite number of solutions.
Each one has x5 and it's free.
Yes, because it had a solution. You have free variables.
And you pretty much
Infinite.
choose what it is.
Choose whatever I want it to be. Okay. Now, they also have some of these H things. Remember the problems that you asked me about the first thing? So let's look at one of those H things. This is number 18. 1, negative 3, negative 2, 5H, negative 7. This is augmented. Find the value or values of H so that the matrix is the augmented matrix of a consistent linear system. Am I on the right? Yeah, consistent. They just want it consistent. Get rid of the 5. So negative 5 times row 1 plus row 2. Negative 5 and 5 is 0. That's 15, so H plus 15. And that's 10 minus 7 looks like 3. I need it to be consistent. Any ideas? What can't happen on this bottom row?
Equal negative.
Right, it can't be negative 15. So H is not negative 15. As long as it's not a 0, as long as that place value is not a 0, this is consistent. So H can't be negative 15. Okay. Questions about what we've talked about so far? All right, let me ask you just some of these thinking questions. Look at number 15. It's an augmented matrix. I drew the little augmented lines on there so I could keep myself straight. Suppose each matrix represents the augmented matrix for a system. In each case, determine if the system is consistent. First of all, decide if it's consistent. And then if it's consistent, do you think it's going to be unique? Remember the little blocks? These are your pivots. They're the ones. The other little stars or whatever's, whatever you want it to be. So, is this one consistent? Yes. It has 3 pivots. Okay, it's got 3 pivots right here. Is it going to be unique? How do you see if it, when it was not unique, when it had an infinite number of solutions, what did it have? What kind of variable did it have? It had a free variable. Is there a free variable in this problem? No, because each column has a pivot in it. X1 is something, X2 is something, X3 is something. It has a unique solution. There are no free variables. All right, what about B? Does it have a solution? Is it consistent or not?
Yes.
So it is inconsistent, correct? I'm hoping y'all are following. Some of y'all are just staring at it. I can't tell if you're following or not. I hope you are. All right, what about this one? Is it consistent? Yes. Is it unique?
I think it is.
Okay, the way you tell if it's unique, how many columns do you have?
Oh, yeah, it is.
All right, you've got, take away the augmented column.
Right.
How many variables do you have? 2.
2.
How many pivots do you have?
2.
2. It's unique. There's nothing free. All right, this part B. Is it consistent?
No.
Not?
I thought it had to have one on the second column, so
Not to be consistent.
that's right.
Remember, the only thing it can't have is if it had a 0 there and a pivot there, that would make it inconsistent. So it's consistent. Is it unique? It's not because, right, this column does not have a basic variable. In fact, that's going to be free. X2 is free because there's nothing there. Okay. All right, true, false. So we'll look at true, false. Give me just, I'm sorry.
Question on
Yes.
that. So if the row has a variable, is it, that's how you gonna say it? Pivot there, it's gonna be consistent if the row,
It's the column,
no, the row.
it's the row.
If the row has a pivot on it, it's
Uh-huh.
gonna be consistent, what you were pretty much saying, or no? Would that be incorrect?
Well, no, because this one, this row has got a pivot on it, but the pivot is in the augmented
Right.
part.
So it's on.
So this and this has no solution.
What could you say if it's not in the
If-
augmented section, it could be?
Yes,
Okay.
yes. If
We're
it's
trying
got,
to think of a way to.
if it has a pivot and it's not in the augmented part, then it's going to have a solution.
Okay.
Does that make sense?
That makes sense.
Okay. All right, y'all want to go through the true and false, or do you want me to just lead you to it?
We need to go through it.
I think we go through it. Okay. In some cases, a matrix may be row reduced to more than one matrix in reduced echelon form using different sequences of row operations. Or is what all the same? Reduced echelon form is all the same, it's unique. So this is false because they stuck reduced in there. Okay. They take reduced out, but it's true. The row reduction algorithm applies only to augmented matrices for a linear system. You can only do this if you have an augmented matrix. No, it's false. Do it to any matrix. A basic variable in a linear system is a variable that corresponds to a pivot column in the coefficient matrix. We have basic variables and free variables. A basic variable in a linear system is a variable that corresponds to a pivot column in the coefficient matrix. True. Finding a parametric description of the solution set of a linear system is the same as solving the system. This is a parametric description. This is what I did to solve it's the same thing. It's true. Do what? Let's see. If one row in an echelon form of an augmented matrix is 0, 0, 0, 5, 0, it's augmented, then the associated linear system is inconsistent.
False.
It is false. If that were a 0 and that were a 5, it would be true. The echelon form of a matrix is unique.
It's reduced echelon.
Reduced is unique. This is false. The pivot positions in a matrix depend on whether row interchanges are used in the reduction process. This is another way of asking, does permuting two rows change your pivot position in the final result at all? No, it does not. So what is it? Pivot positions, that's false. They do not depend on whether you do interchanges. Reducing a matrix to echelon form is called the forward process of the row reduction process. Forward phase of the row reduction. Doing the backward puts it in reduced echelon form. This just said echelon form, so it's true. See, I told y'all they're going to leave words out and put words in. Be careful. Whenever a system has free variables, the solution set contains many solutions. False. Why is it false? Does anybody know why it's false? Whenever a system has free variables, they're saying no matter what happens, if you've got free variables, it's going to have a solution. The answer is false because they forgot to say if it's consistent and has free variables, then it has many solutions.
I just like shooting us in the foot.
They do. They do. Okay. A general solution of a system is an explicit description of all the solutions of the system. An explicit, true. This is a description of all the solutions. It's true.